next talk, let's welcome two of my dear friends from our own Alluxio, Bin Fan and Alluxio. Bin is the founding engineer and VP of open source at Alluxio. You guys probably see him a lot here on Slack. He's also the co-chair of this Alluxio Day event. Prior to Alluxio, Bin had worked for Google for building the next generation storage infrastructure and received his PhD in computer science from Carnegie Mellon University on the design and implementation of distributed systems. Lou has been involved in open source software for many years and is currently a software engineer at Alluxio. Lou has developed easier ways for Alluxio integration in the public cloud environment, and she is mainly responsible for leader rejection, journal management, metrics management, and big data preparation for machine learning workloads. She has received her MS degree from George Washington University in data science. And many of you probably know that Bin and Lou are both quite active in our community Slack, helping users for their questions. If you're not familiar with Lou, if you join us on our Monday, usually we have a community developer sync. Those are open to everyone. You will have your conversation with them. So if you have any questions by then, you can also join us then. So now, without further ado, let's hear from Bin and Lou on Alluxio data orchestration for machine learning.
Okay, thanks, Jasmine. Okay, hi everyone, I'm Lou, and I also have been here, and we are going to share more about the Alluxio data orchestration for machine learning workloads. I think that Jasmine just introduced ourselves, so we don't need to do it ourselves. That's great. So for today's agenda, we will mainly focus on three parts. The first part that I will introduce what is Alluxio POSIX API and also how to use this API. I think Peter has done a great job introducing some part of it, and I will give more details of this API. And Bin will later on, he will introduce some of the latest work and roadmap regarding how to fit Alluxio POSIX API into the new machine learning world. So the first question, what is Alluxio POSIX API? So for POSIX, it's also called Portable Operating System Interface. So basically, it's a standard that makes things stay compatible in operating systems, which means that if you change from one operating system to another, you can use the same bash scripts, you can run the same applications, you can use the same shell commands. So POSIX standard helps you to use the same APIs in different operating systems. So as you guys may know that for when you're using Alluxio, you can actually use the same Alluxio API to access different storage systems like HDFS, like S3. So you change from using N APIs to one Alluxio APIs. But Alluxio POSIX API made one step further. It actually allows you to interact with all your storage systems that using your local file system ways, which means that you can use or interact with all the storage systems just like your local directories. And for your data application, they can just treat all those storage systems just as the local data source. They don't need to modify their scripts. They don't need to modify the data applications. So that's what me. I think Peter already presents so good in this field, but I want to emphasize this part. So basically, we are able to mount different storage systems into Alluxio namespace, and then mount Alluxio as a local folder. In this way, you are able to accessing the remote and distributed data just as your local directories. So another benefit actually provided by Alluxio itself, considering that you have a large object storage that maybe contains petabytes of data. And if you put all the data into each machine, each disk, it could be like pretty expensive. You may need to use a lot of disk space and a long time of transfer those data to those disks. And with a disk crash, it's disaster. But by using the Alluxio servers, we can actually only cache the hot data that actually needed for your training job. Maybe you have petabytes of data, but maybe only several GB or TB of data is actually needed for your training jobs. And also, Alluxio helps you to break the big objects into multiple smaller blocks. So it can store those blocks in different servers. So usually for your training job, you only need to get your data from the local machine or the nearby machines instead of going to your object store to fetching data every time. So by using this way, you can keep your really expensive GPUs busy and then save the money for saving the data in the Alluxio servers. So how Alluxio achieve those amazing things, like how we are able to allow you to retrieve the remote data locally, just like your local folder. Under your hood, there is something called FUSE. It's called the file system in user space. It basically allows us, the software, that can easily create our own file system without worrying about the really complicated kernel codes. What we only need to do is actually implement an interface that provided by the libfuse. So we don't need to care about how the user code goes through the kernel. What we only need to care about is what our desired behavior for each read operation, each write operation, each ls operation. We only need to define our desired behavior. So that's an example of what's showing here. So we actually, when a user, they want to create a directory, and all those user information and the path that you want to create will go through the very complicated virtual file system, also the kernel code, and then eventually it will go to call the libfuse make directory call. And libfuse, we go back to actually call Alluxio fuse. So say, hey, we want to create a directory. And then Alluxio fuse will receive that information, and it will tell the Alluxio master that, hey, somebody want to create a directory, and then we create a real directory in Alluxio. And if you mount it like S3 into Alluxio, that directory will be created in the S3. There are many benefits of Alluxio POSIX API, like you can use it as local folders, and we provide some caching ability and all the data management tools that are provided by Alluxio. But there are also some of the limitations of Alluxio POSIX API. And just similar to the advantage brought by Alluxio, do have some disadvantage that also brought by Alluxio. And because Alluxio is designed as a write once and read many times file system, so the files can be only returned only once, only sequential, and never be modified. So if you try to do something in the shell command that try to truncate the file or append the file after you already finished written it, so those operations will not be supported. And also, as Alluxio is a file system, but it does not have the concept of hard links or soft link. So if you want to do operations that are related to those soft link and hard link concepts, those operations are not supported. And because Alluxio POSIX API is built on top of FUSE, so our performance is bounded by the FUSE implementation, bounded by the underlying libfuse and the FUSE kernel code. And also because Alluxio POSIX API, you can consider it as a long-running Alluxio client. It will actually call our client code and to talk with our Alluxio master and workers. So its performance is also bounded by the Alluxio client performance. Although that we have some of the recent jobs that try to get around the FUSE and Alluxio client performance bottleneck. And the next topic is that how we can use the Alluxio POSIX API. So always check out our official documentation about the POSIX API. There's detailed instruction to get you on the API. But basically, there are several steps. First, you need to have a running Alluxio server and install the libfuse package in your Linux environment. And then you can run the Alluxio fuse command to actually mount an Alluxio path to your local mount point. And then you can use the stat command to check out your local mount point status. After you're done with everything, you can feel free to unmount your mount point. So after you mount Alluxio to your local mount point, you can actually interact with Alluxio namespace and interact with all the UFS that backed by Alluxio using some of the shell commands like the cap here. And also you can run some of the TensorFlow training job that using your local address just as your data source. So we actually have a short demo of how to actually use Alluxio POSIX API. So basically, before you try to mount Alluxio FUSE, the first step is always that you need to have a running Alluxio servers. That's the running Alluxio master and running Alluxio worker process. And then we need to make sure that your HDFS or the S3, your under storage systems is mounted to Alluxio, so that you can interact with those under storage systems through Alluxio. For here, we actually mount HDF storage to our root, Alluxio root. And there is already some files that existing in Alluxio. The data directory is actually exists in Alluxio. And inside this data directory, there are actually some pre-created test files that already exist in the data directory. And those files are not only existing in Alluxio, but it also existing in our underlying HDFS storage. Now we're trying to see is that how can we interact with the Alluxio namespace and interact with the underlying HDFS through Alluxio FUSE. Now you can see we can mount the Alluxio root to the local mount point called NNT FUSE through the Alluxio FUSE mount command. And you can see that we successfully mounted Alluxio path root to the local mount point NNT FUSE, and there is a running Alluxio FUSE process. Now we're trying to see more information about this Alluxio FUSE mount point by running the stat command. You can know that which Alluxio path is mounted to which local mount point. Now we are finally going to interact with the local FUSE mount point. You can see there is a data directory in the FUSE mount point and the test files that which we just view through the Alluxio commands and through the HDFS command. You can interact with them just like your local folder and local files. And now we want to do the reverse things. Instead of viewing the data that exists in HDFS and existing in Alluxio, we want to actually make changes to those HDFS and Alluxio through the local mount point. We can create a directory here called the FUSE directory. Just use the local mkdir commands. And then we can actually create a real test file. Here we create a FUSE file for 10 megabytes. Now we are going to see that, okay, the changes that we are making to the local FUSE mount point, does it actually make changes to our Alluxio namespace and the HDFS that backed by Alluxio? Now we run the Alluxio command to check. Okay, we can see the FUSE directory is here. Now if we go into the FUSE directory, we can see the file that we just created by interacting with the local folder. If we check the HDFS, we can also see the similar data here. So that's how you interact with the Alluxio POSIX API in order to interact with the Alluxio namespace and all the storage systems that backed by Alluxio. In our example, feel free to change HDFS to S3 or Google Cloud Storage, whatever storage system that you need to use. Okay, now I will hand this to Bing, who will introduce our new really exciting Alluxio POSIX API evolutions in the new machine learning world. Hi, Bing.
Thanks, Lu. Thanks for the great talk. Let's go to the second part of this conversation for this presentation and talking about the few optimizations we're adding to Alluxio FUSE. Yeah, next slide, please. So originally libfuse, you may know that libfuse or the FUSE system is implemented in C in native code. So in order to let Alluxio talk to libfuse, you have to use a certain bridge or some glue code to make sure the Java logic, Java methods can be invoked in the C land. So originally we were using a third-party library called JNI-FUSE, which is maintained by some other open source projects. And because this open source the third-party open source library was not updated that much, and we are not being able to debug very deeply into this core stack. So around like May or April last year, we decided to create a new implementation based on JNI. The difference between JNI and JNR is kind of like a subtle, so I won't go to the details of like why we go in this decision. But essentially, this choice enable us to directly add more optimizations because we have more control in this stack, but also provides more closer performance to the native libfuse performance. And also one of the key reason for this is because we want to support high concurrent workload, and the original JNR-based FUSE library is not well supported in this case. The very last reason is easier to debug, as shown in this slide. With JNR FUSE, there's a lot of code involved and a lot of extra dependency involved. Makes us very hard to do more optimizations and debugging. So we just try to make this stack thinner so we can have a better control over this stack. Next slide. This page shows how we can benchmark the JNR FUSE and see how it scales. We're adding more threads on the workload generator. As you can see here, this shows you the megabytes per second. This is in a very early experiment we're doing when we're developing JNI FUSE. The blue curve on the top is the native JNI FUSE performance, and the red curve is benchmarked using JNI-based FUSE, and the JNR FUSE is shown as the bottom curve. As you can see, in the beginning, when we were adding relatively small amount of number of threads, the JNR FUSE, JNI FUSE, or FUSE, they are pretty close, and you can understand there will be some performance overhead when we're adding JNI or JNR, the translation layer here. But what's happened is after we are adding more than 8 threads, total threads accessing this mount point, the JNR FUSE performance drops badly. So it's just crashed. And our new implementation of JNI FUSE is still keep growing until like we hit 6 process times 6 threads per process, which is 64. 8 process times 8 threads per process equal 64 threads in total. So the JNI FUSE is getting pretty well performance compared to FUSE. Next slide. And I want to really echo here and appreciate the community help, community collaboration to create this new JNI-based FUSE library. And it's initiated by Alibaba and the Nanjing University, researchers from Nanjing University. And then it's a deep collaboration with Alluxio and also engineers from Tencent, and also like Microsoft engineers contributed here. And this is already although it was a pretty new feature, it's already being used by companies like Microsoft Analytics Aspects, as shown in the previous talk. Next slide. Okay, so that's so much for the JNI-based FUSE. We want to just talk about the latest optimization we are still working on, and which will be available soon in 2.6. Next slide. So one motivation actually asked already on the platform is whether we are using 2 processes, a FUSE process and a worker process, or that's a single process. But prior to 2.5.0, these are 2 different processes. You can think Alluxio service is a standalone set of workers or standalone set of servers, and the Alluxio FUSE is a separate process, which you can think it's a long-running client sitting there translating the POSIX API calls into Alluxio API or Alluxio client API calls. And in case you have your local data, you have data stored in local cache, which is a cache hit case, you still need to have some RPCs to coordinate the Alluxio client, which is a FUSE process, and Alluxio worker. So they can coordinate, they can notify each other. And in the case of you are reading a large amount of files, this is okay. And because the overhead in this communication is amortized. But in the case you're reading a large amount of small files, which is very commonly seen in our targeted workloads like in machine learning training, reading a ImageNet. This is quite common, becomes a performance bottleneck. So that's the driving. This is the motivation for us to start thinking combining these two processes to particularly speed up the training speed when reading many small files. And this work was done in the past months and was already merged into Alluxio codebase. And as a result, you can turn on, in addition to supporting the original way running Alluxio FUSE, you can also start Alluxio FUSE mount points by adding a flag when you are launching Alluxio worker. And as long as Alluxio worker is launched, you can see, and the configuration is correct, and you can see a mount point added by this Alluxio worker into the local file system namespace. So this is really easy, and according to our current benchmark, and the performance is also pretty good. Next slide. Yeah, this shows you how to configure and launch FUSE on worker. Just add, actually only the first flag is required. Alluxio.worker.fuse.enabled equals true, as long as you are using 2.5.2 or later. And then you can start the Alluxio process, and you will see Alluxio namespace exposed as a local path called /mnt/Alluxio service as configured there. Okay, that's so much for the current optimization, including combining Alluxio worker and the FUSE process to eliminate local RPCs, and also the new JNI-based Alluxio FUSE integration. We're working on a few more things. Some of them is already done. For example, we make this JNI-based FUSE library a module. So this is very easy to use, even like for projects outside Alluxio, and this is contributed by Tencent. We also plan to work on, so we already work on the case optimizing the performance when you have a local cache hit and you don't have to get local RPCs. But in case you don't have this data, you are not fortunate to have this data cached on local worker, but this same data is cached, can be provided by another remote Alluxio worker. In this case, you can still read from the Alluxio remote Alluxio worker as we call this a remote cache hit, instead of reading data directly from the under storage like S3. In this case, this will be the next target for us to do some performance optimization, and especially we identified certain some room to further improve the gRPC performance because we're using gRPC to communicate between workers. And we also plan to support Alluxio, to let Alluxio support FUSE, libfuse 3.x. And this will give us a lot of flexibility setting different configurations and also potential performance boost because the upgrade of this libfuse itself. So, and many more to come. Like, for example, we're thinking introducing RocksDB for some storage engine to even reduce the performance overhead reading and writing the data on a local worker. So if you're interested to understand the latest updates for this performance optimization, or you have some other ideas you want to contribute to this open source project, you're welcome to join a weekly community sync to create this solution together. Next slide. Yeah, so we will share this later, but this is a list of reference so far. We have, it's still a pretty early project, a pretty new project. So we are still working on adding white papers or reference architecture, but these are the existing references if you are willing to learn more. Next slide. Oh, okay. Some words are missing here. So we're hiring here, and welcome to join the Alluxio community. If you are interested in either joining the community, join the Slack channel. If you are interested to work with us, we're expanding actively, and you can contact me together directly. Thank you, and I'm willing to open the floor and taking questions.